Welcome back. This is lecture 36. So in the previous lecture we started seeing the frequency response of our common source amplifier, and the genesis of the frequency dependent characteristics of the common source amplifier was due to the inherent capacitances associated with the MOSFET. So before yesterday's lecture, or before the last lecture, we kind of ignored the capacitances of a MOSFET, but in a design we cannot really ignore them, right? So since we cannot ignore them, we need to understand the contours till which the common source amplifier will work with regards to the frequency with respect to if the input is frequency varying. Okay, so then we saw that there are capacitances associated with the gate to source, capacitances associated with gate to drain, drain to body, and so on, right? So, and then we sketched our small signal equivalent of the common source amplifier, right? And this is what we saw. And we ignored the channel length modulation. I mean, you can as well put that back, just that what will happen is the load resistance RL will get slightly modified as RL parallel the R out. Okay. And we also have CGD. And then we said that, I mean, we'll treat the, I mean, let's figure out what's going to happen due to the capacitances CGS and CDB, and we'll talk about CGT in one of the later lectures, right? So let's continue doing that. And then we spent some time understanding the frequency response of VGS with respect to VI, right? So, and we saw that VGS J omega or VGS of S, the Laplace domain, can be represented as the DC gain, or the gain at the, or the transfer function at DC, which was RTH by RTH plus RS times 1 by 1 plus S by P1, where P1 was 1 over the time constant associated with the capacitance C1, right? This is T1, tau 1, which is 1 over CGS times RS parallel, right? Then we saw the Bode approximation of the same. So essentially, let me write the thing down once again. VGS over VI was and the Bode approximation of this was if this is omega, right? If this is omega and y-axis is our is in dB, right? This is mod of Vg or Vi, and this is in dB, right? So this is 20 log. Okay, so at DC we'll have, this will be 20 log of RTH by RS plus RTH, and this is less than 0 dB, right? It's, I mean, if this is 0 dB, this will be, since this is less than 1, so in dB scale this will be less, this will be negative, and this will be flat till some frequency P1, and then it will go down at a slope of minus 20 dB per decade, right? And this will be the magnitude plot. And what will be the phase plot? the phase plot will also be something similar. That is, it will start from 0, right? So it will start from 0 at P1, at pole P1 it will hit minus pi by 4, and at infinite frequency this will saturate at minus pi by 2, right? Okay, so and the exact expression for the frequency characteristics is the following. Okay, so if we spend a couple more minutes on this topic, so if I tell you that what will be VGS, if Vi, let's say Vi is equal to Vp sine omega naught t, right? And I want to plot VGS in time domain with respect to time, right? So let's say this is the input. So let's say this is, so let me draw one cycle. Right? And this is going on forever, right? So it's a steady state response. So we cannot assume that the input has just started. Input has started some long time back. Okay, so let's say this is Vi, and let's say omega naught, in this case omega naught is equal to let's make some assumption. Let's say P1 is equal to 10 megahertz, right? And let's assume in this case omega naught is 1 megahertz. Okay, fine. So what do you think will VGS look like, right? So I want to plot VGS. So clearly we are in the Bode plot. Where are we? We are somewhere here, right? We are somewhere this side. We are below P1, right? We are 10 times below P1, which means if we have to do Bode approximation, what are we essentially saying? We are essentially saying that the output is the transfer function is equal to the DC characteristics, right? Whatever VGS we'll observe when we are at much lower frequency than the first pole is equivalent to the case where the pole didn't even exist, which means the capacitor didn't exist. So if the capacitor didn't exist, what would have been the amplitude of the output? It will be the input amplitude times RTH by RTH plus RS. And let's make life further simpler, and we say that RTH is much greater than RS, which means in this case the input will be, amplitude of the input will be exactly equal to the amplitude of the output. All good. But what about the phase? Where are we in terms of phase? What is the phase? Phase is, angle is minus tan inverse omega by P1, right? So if you are much at a lower frequency than P1, then we can as well say that the phase is also minus tan inverse a very small number, which is much less than 1, which means you can approximate it as 0, right? So which essentially means that the output will essentially track the input all the way, right? Okay, so this is for P1 equal to 10 megahertz. Sorry, this is at omega naught equal to 1 megahertz and P1 equal to 10 megahertz, right? Okay, so let's do another one. Let's say omega naught is equal to 10 megahertz. That is, omega naught is exactly at the pole frequency. or rather exactly, yeah, exactly at the pole frequency, right? So let's sketch the same thing again. Let's resketch, right? Okay, so firstly let's draw the input first. Okay, so if omega naught is a 10 megahertz, if I have to draw the same thing in same scale, what will the input look like? So the case on the top is omega naught equal to 1 megahertz. The case that I am trying to draw is omega naught equal to 10 megahertz. So in the same scale, I will have 10 cycles of the input, right? So essentially, or in other words, I should have 5 cycles within the 1/2 cycle of the top plot, right? So let me break up 1, 2, 3. It's not happening. So 1, 2, 3, 4, 5. Okay. So let's see. Let's say, which essentially this will mean that the amplitude will be the same. One, two, three, 4, 5, I guess, right? So approximately we have 5 cycles, and this is, sorry, I think I made a mistake. My drawing is pretty bad here. So you have to break this guy up into 5 cycles, 5 parts. So let's see, this is 1 part, this is 2 part, 3 part, 4 part, and this 5 part. So have 1, 2, 3, 4, 5, right? Still doesn't look good, but you get the idea. Okay, so if this is the input, what will the output? What will be the output amplitude? If omega naught, if I use Bode approximation, then at P1 also it seems like just below P1 I have the gain is that of DC gain, but just above P1 the gain is kind of dropping. But we know better. We know that at the frequency of P1 I will have a 3 dB drop, right? So the amplitude will be 1 over root 2 times that of input, right? But more critical thing is happening in terms of phase. What is happening to the phase? The phase at P1 is minus pi by 4, which means that our output will be delayed. Our output will be delayed by 45 degree, right? So in other words, we'll have something like this, right? So this is delayed by 180 degree, this is delayed by 90 degrees, somewhere they are delayed by 45 degrees. So we'll have something like, and so on, right? Okay, fine. And the amplitude will be 1 over root 2 times that of input. Okay, and what's going to happen, let's say at very high frequency, right, at omega naught much greater than P1 or much greater than 10 megahertz, what's going to happen? In that case, obviously, I mean, I am physically not equipped enough to sketch the input with such high number of oscillations within a same period, right? So let's just assume that this is it. So this is the input, right, and so on. So what will the output look like? Firstly, where am I talking about now? I'm talking about the scenario where I'm far away from P1, right? Or let's say if I say that this is like 10x, right? Omega naught equal to 10 times P1, let's say omega naught equal to 100 megahertz, let's say. So then for all practical purposes, I can say that the input has almost died down. There will be a very small amplitude, right? However, there will be a delay, there will be a phase lag, and how much will the phase lag be? The phase lag will be that of 90 degrees, right? So the phase lag cannot be more than 90 degrees because this is a first order system. That's all it's saying, right? So essentially we'll have something like this and so on. Okay, so if I have to blow this up, this is what's going to happen. Let's say we are still getting omega naught equal to 100 megahertz case. So let's say your input is, one cycle is something like this. Your output will be 90 degree delayed, so is quarter cycle delayed, right? And will be of very small amplitude. Okay, so you get the idea, right? So this is 90 degree delayed and reduced in amplitude, right? So this phenomena of different delay and different amplitude will be of a lot of interest as we move forward when we talk about stability of feedback systems. So this, I wanted to give you a intuitive feel of what we mean when we say that there is a frequency dependent component and we have certain phase and we have certain amount of certain magnitude response, right? This is obvious, and we have all done phasor systems, phasor analysis in the past, but this is a quick refresher. Okay, fine. So this is as far as the dependency of the input is concerned. So now let's concentrate on the output side, right? So let's say this is VGS, and we know what is the VGS. So let's say this is VGS of S. Right? So this VGS of S got generated because we have some stuffs connected to it, right? Now we want to find out. What is the final output, because that's what the goal is. Okay. This is CDB. Okay, so if we use the same framework as earlier, right, what should we see? What we should see? We should basically say that V naught S will be GM VGS of S. This is the current minus of that divided by the conductance at the output, and the conductance is GL plus SC. Right? Okay. We can also express this in terms of in terms of DC gain, DC transfer characteristics, and the associated poles. And if you have to do that, what do we need to do? We basically then say that this is equal to minus Gm by Gl times Vgs of S times 1 by 1 SC dB times RL, right? So in other words, this becomes, or in other words, V naught over S, V naught S over Vgs S becomes minus Gm over Gl or minus Gm RL by 1 by 1 plus S by P2, where P2 is equal to 1 by capacitance, or 1 by the time constant associated with the with that node, times 1 over the time constant associated with the node. The time constant is essentially CdB times RL, right? Okay, fine. So what is this again? So could we have written this without writing out the entire transfer function? Could we have written this in terms of the framework that we have developed? Yes, we could have, because what is this? This is the gain. This is the gain at very low frequency. This is the transfer function at DC times some frequency dependent part, and the frequency dependent part can have a zero and can have a pole, right? Or can have multiple zeros and multiple poles. We haven't yet talked how to identify if there is a zero or not. So, but since we know that this guy doesn't have a zero, so let's keep the discussion on the zero aside for the time being. But do we know how many poles we have? Yes, we know, because we have, this is a one capacitor circuit, one capacitor and bunch of other non-frequency dependent elements, which means we have one pole. What is the frequency of the pole? The frequency of the pole is that of 1 over the time constant. We know how to find out time constant. Time constant in this particular case is CdV times RL, which means we know the transfer function, correct? So what, at the end of the day, what becomes V0 over Vi? What is V0 S over VIS? This becomes RTH by RTH plus RS times minus GMRL times 1 by 1 plus S by P1 times 1 by 1 plus S by P2, right? Where P1 is equal to 1 by excuse me, 1 by time constant associated with CGS, right? So this is tau CGS, and P2 is a time constant associated with CdV. This is tau CdV, which I know tau CGS is equal to CGS times some equivalent R, some Thevenin equivalent resistance, and CdV times tau CdV is CdV times RL. Okay, so now can we sketch the Bode plot? So if I have to sketch the Bode plot, what should it look like? This is, let's say I sketch mod of V0 over Vi in log scale, that is 20 log, or I'll drop writing log scale every time. We'll assume that this is log scale, right? So we'll assume log scale, right? So this side is log scale. If that is the case, then what is the gain at very low frequency? And let's further assume that P1 is less than P2, right? Let's assume. So there is no guarantee that P1 has to be less than P2. So let's assume P1 is less than P2. This is assume. So it helps us in marking of the points. So let's say this is P1 and let's say this is P2, right? So if GMRL times RTH by RTH plus RS is is much greater than 1, right, or at least greater than 1, and let's further assume RTH is greater than RS, so this doesn't load, so that the gain at DC is GM times RL, so that's what we get here, GM times RL till the frequency P1. Then between P1 and before P2, what is that new transfer function? So using Bode approximation, so what is V0 over Vi with omega is greater than P1 and less than P2? What will that be? So that will be the I. So what we are essentially saying is that in this case, I am omega is greater than P1, which means the S plus P1 term, S by P1 term will dominate using Bode approximation, right? So this becomes RTH by RTH plus RS, and if I am doing mod, then this times GM times RL, this is, let's say, mod, right? Then it becomes 1 by S by P1 times 1 by what? 1 plus S by P2, but in this case omega is less than P2, so using Bode approximation I am neglecting the S by P2 terms, this becomes this, right? So essentially it still is a 20 dB per decade roll off, right, similar to what we had earlier. So this becomes, right? Then what's going to happen? Then when we are at P0 over Vi, omega is greater than P2, then what will be the transfer function? The transfer function will be RTH by RTH plus RS times 1 by S by P1 times 1 by S by P2, which means I have a SS squared term, right? And so the roll off will be at 40 dB per decade. So this will be something like this. Okay, so here the transfer function essentially becomes GM times RL by S by P1, and here this becomes GM times RL by S by P1 times S by P2. Right? Now what about the phase? What about the phase? What about the phase? What about the phase? The phase will start from 0 as usual at P1. If P1 and P2 are separate, far away, I mean the phase at P1, let's say, is not getting affected by the phase of P2, right? So we'll get, so let me also write out the phase first. Phase expression will be minus tan inverse omega by P1 minus tan inverse omega by P2. And if we assume that P1 and P2 are separated and they are not interacting with each other, which means that when I am at omega equal to P1, I am far away from omega equal to P2, which means the phase will be minus 45 degree. So this is minus pi by 4, and then it will reach minus pi by 2, then again it will go by additional minus pi by 4 and settle at minus pi, right? Okay, so that's what the phase will do. And what impact will that have on our transient response? Just that you will see that now the maximum delay, that the maximum phase delay that we could have had at very high frequencies would have been only 90 degree, but now we can have 180 degree phase, maximum phase delay, which means there can be a half cycle delay of the input at max at very high frequencies, right? What is very high frequency? In this case, it is at frequencies much higher than P2, right? Okay.